Thank you so much for joining us for our April meeting. I've been ecstatic ever since I checked the forecast and saw that it was going to be clear finally, and coincides with one of our monthly club meetings. So you're in for a treat after the presentation. We'll go outside with the telescopes and take a look. We should be able to capture Jupiter, Mars, and maybe the moon. I don't recall. But in any event, we have a very awesome presentation today titled Ultra-Faint Dwarf Galaxies, Their Evolutionary Histories and Galactic Correlations. And so this presentation is being given by our guest presenter, Dr. Katy Rodriguez Wimberly, Assistant Professor, California State University, San Bernardino. You can also follow her on Facebook and Instagram, and I think Twitter as well, at Astronomy. So Dr. Katy Rodriguez Wimberly is an assistant professor of physics and astronomy at CSU San Bernardino, specializing in near-field cosmology and the evolution of ultra-faint dwarf galaxies. A passionate advocate for equity in STEM, she serves as director of mentorship for the CalBridge program and sits on the Astronomical Society of the Pacific's board of directors. A first-generation college graduate and Southern California native, Katy's journey spans Mount San Antonio College to a PhD from UC Irvine and a prestigious NSF/MPS Ascend Fellowship at UC Riverside. Outside academia, she enjoys hiking, anime, and adventures with her two young children.
Yes, I'm so excited to chat with y'all today about ultra-faint dwarf galaxies. Not many people, not even in astronomy, not many people have heard of them because they're very, very small. We'll get to that. So I guess I'll just go. If you have questions, I'm happy to answer them during the talk or even hold them till afterwards. So without further ado, thank you so much for having me. And oh, there we go. So what do I mean by ultra faint, right? So I want everyone to take a second, and I know I can't see you if you actually are closing your eyes or not, so I'm just going to trust that you close your eyes for just a second and think about a galaxy. What do you see? What shape is this galaxy? What colors are in the galaxy? Just take a second to think about what galaxies look like. Okay, so who saw something like this? A big, bright, it's kind of round, there's spiral arms, there's lots of like gas and dust and stars and activity within that galaxy. This is what kind of everyone thinks a galaxy looks like, because many of the galaxies that we see in the night sky, with everything from the unaided eye to binoculars to giant, the largest optical telescopes in the world, we see these active star-forming spiral galaxies like this one, the Southern Whirlpool Galaxy. What I mean by ultra-faint galaxies are these things. I promise that is a galaxy. This is an ultra-faint dwarf galaxy. It's called Leo 4. So this kind of circular-ish yellow dashed line in the kind of larger background picture is the extent of where we think this galaxy kind of lives in. That zoomed in square there, which was taken by the Hubble Space Telescope, shows the inner regions of the galaxy. I have a few kind of diagrams in a little bit to explain more about why we think this is an actual galaxy and not just a pretty picture of the night sky. But this whole talk, I'm going to really hopefully convince you all that these tiny, tiny, very faint galaxies are some of the really most exciting galaxies in the whole universe. They're also ultra small. So you may be familiar with this kind of like 2-scale model of our solar system, where if Earth is this little marble here, like really the size of a marble, and then you think of the sun and it's this giant kind of sphere or ball or something like this, right? But hold those kind of size comparisons in your head, a little tiny marble and a really big like beach ball. Keep those in your head. If instead of the little marble being Earth, if we think of the little marble as an ultra faint dwarf galaxy, then the giant beach ball, which is the sun in the old model, that would be the Milky Way. So these ultra faint dwarf galaxies are tiny compared to our own galaxy, the Milky Way. And just as one more kind of point of reference there, the Milky Way is a medium-sized galaxy. So there's things that are 2, 3, sometimes 100 times larger than our own galaxy. Ultra-faint dwarf galaxies are much, much, much smaller than that. So ultra-faint, ultra-tiny, and actually, partially because of this, they're really hard to see in the night sky. You all saw the image a moment ago. All of the ultra faints that we have seen so far, about 50 of them, are satellites of the Milky Way, of our own galaxy. So since the dawn of humanity, we've known of the large and small Magellanic Clouds because you can see them in the night sky in the southern hemisphere. And then throughout the 70s, 80s, 90s, we started discovering other galaxies that orbit our own. Those blue dots we call the classical dwarves. They're much smaller than us, but they're not tiny. And you can see them with just kind of almost any telescope, depending on the conditions and location and all that good stuff. I'll play this one more time, because what happened in 2005 was we created these all sky digital surveys. So telescopes that just automatically automated, they look through the night sky just over and over and over, and we use kind of like machine learning algorithms, like baby AI in a sense, to look for what we call overdensities of stars. And so that's why in 2005 you see this crop up of all of those red and green dots in this video, because those are the ultra faint dwarf galaxies. Those are clumps of stars that through different types of observations and studies, we can tell that they're orbiting one another. And I'll go into that in a little bit. But we've seen now there are tons of galaxies nearby us that we've never known before. It's just been about 20 years that we've really started to see the great wealth of galaxies in our own galactic backyard. So I wanted to take a second to just kind of talk about this idea of a satellite galaxy. Just like the Earth and Mars and all of our planets and asteroids and comets are orbiting around our sun, there are galaxies that orbit around other galaxies. So if we think of a galaxy like this, bright, star-forming, happy galaxy, we actually believe that every galaxy lives within a sphere of dark matter, or a dark matter halo, as we call it. We know there's dark matter out in space, and we can see that it kind of clumps around galaxies. And actually, we think the dark matter formed first and then the galaxies formed within it. But regardless of how large or how much star formation is going on within a galaxy, we think every galaxy lives within its own dark matter halo. Now, so we have an ultra faint dwarf galaxy here in its dark matter halo, and a big, bright, star forming galaxy in its own dark matter halo. And as these things are all moving about the universe, what we see is that some of the smaller ones will be kind of gravitationally pulled to the larger ones. And once a small galaxy has fallen into the dark matter halo of a larger galaxy, we classify them differently. So the larger galaxy now is a host galaxy, and all the little smaller things within it are satellite galaxies. So we used to know of only 2 satellite galaxies, the Milky Way, the large and small Magellanic Clouds. And then in the 80s and 90s, even some of the 70s, we started to see a roughly 10 classical dwarf galaxies. that are satellites of us. And then after 2005, we saw like we're up to like 50, going on 60, depending on your classifications. So we have all of these satellite galaxies that are just orbiting around the Milky Way, but they're very cosmically close to us, so we can study them in a really great detail, like look at their individual stars. So we have these ultra faint, ultra small galaxies that are all satellites of the Milky Way, at least the ones that we've seen so far. And what I think is really, really amazing about them is that we think these are fossils of the very first galaxies ever formed. So this is like galactic archaeology. And we think this because all of the stars are really old, like 11, 12, 13 billion years old. So they're basically formed when the universe was forming into what we know of it today, right? So these are very, very ancient. Because they're so old and so universally old, and they all look the same, we can use the population of ultra-faint dwarf galaxies as a tool in what we call near-field cosmology. So y'all have probably heard of cosmology and how it's really the study of like why things are the way they are, right? Why did our universe come to be, and the Big Bang Theory, and the James Webb Space Telescope doing all of this amazing observations, and astronomers doing tons and tons of studies showing that maybe what we think about cosmology is all wrong. We don't know. We'll see. It's an exciting time in astronomy. We may be wrong. It's a scientist's favorite thing to be wrong. At least my favorite thing to be wrong. It means I'm learning. Sorry, aside. So near field cosmology is this idea of, instead of trying to look back as far as we possibly can, which is what JWST is doing, near field cosmology looks really, really close to us at really old things. So it's kind of another way of saying galactic archaeology, right? Near field cosmology. We're looking at what's close to us to try to learn about the early universe. And these ultra faint dwarf galaxies are a fantastic way to do that. But we first have to kind of decide if these are fossils of the first galaxies ever formed, if they're true relics of those first galaxies. And I've kind of put 3 criteria on that. So first, these kind of, as I mentioned earlier, overdensities of stars have to actually be galaxies, right? And I'll go into each of these points. So we want them to actually be galaxies for them to be a fossil of the first galaxies. We want them to really not have evolved or not changed much since the early universe, so that we can really use them to study and learn about the early universe. And this also means that they can't really have much interaction with larger galaxies that they've passed by over their lifetime. Now, they're all satellites of the Milky Way, as I've gone on about, which means that they've had some interaction with the Milky Way, but we can do some work to quantify like how that interaction has changed what we're seeing, and how, changed how they were, from the early universe. So 3 criteria that we want to meet for our ultra-faint dwarf galaxies to be true relics of the first galaxies that ever formed. So let's look into this first one. We know that there are other tiny, beautiful clusters or overdensities of stars in the night sky. Some of the most famous ones are globular clusters. These are just 3 examples. These are like these basically beautiful collections of like diamonds in the sky, right? They're so gorgeous. And they're actually about the same size as ultra faint dwarf galaxies. So often when we're kind of characterizing these, we have to do a lot of tests to make sure that these ultra faint dwarf galaxies are not just faint globular clusters. And I'll get into that. But visually, it's kind of easy to compare because you have big, bright, beautiful globular clusters and you compare those to ultra faint dwarf galaxies, and it's fairly easy. Because they are so faint. Most of the reason they're faint is because unlike globular clusters, all of the stars in our ultrafaints are very old, and so they're much dimmer compared to younger stars that are much brighter. So that's one of the ways that we can kind of classify it. Make sure it's not a globular cluster or something like an open star cluster. The way we do that in the kind of quantitative sense, right? Like, let's put numbers to this instead of just visually comparing them. We look at the kind of magnitude, like how much light it's giving off. So that's this, this is one example of an ultra faint dwarf galaxy, Ursa Major 1. And we do look at, does this group of stars look like our theoretical models, right? At least in how much light they're giving off. So this red line is a theoretical model of a really old set of stars, and Ursa Major 1 mostly falls on that line, right? Again, we want to make sure that they're like actually orbiting each other, so they have to be physically close to each other. This kind of B plot here is literally just a like sky map of where those stars fall. And you can see there's like the X's and the little squares, and those are all not member stars of Ursa Major 1. So there's a little bit of work to kind of tell, like, are they actually physically close to each other? And the primary way that we really think about galaxies versus globular clusters versus stars that are just kind of close to each other is looking at their velocity. So if a galaxy is living within a dark matter halo, the stars within that galaxy are really similar to one another, much more so than even compared to like globular clusters, right? So you can see here all of these kind of red histogram bars. Those are all of the member stars in this Ursa Major 1. So we look at the light that they're giving off, what we call color. We look at how close they are together, and then do they have the same velocity, which really gives us a hint that they are orbiting one another or some center, right? So that's how we really classify and determine whether a group of stars is a galaxy or a globular cluster. Most of these ultrafaints are galaxies, or at least some kind of remnant of a galaxy. So we've checked off number 1. But let's keep going and looking at evolution since the early universe. So what's really cool about these is that they all kind of have these, what I said, ancient stellar populations. So these kind of 6 figures here, these show on the horizontal axis. These are the age of the stars in these galaxies: Bootes, Hercules, Canis Venusente, Leo, Coma Berenices, and Ursa Major 1. We name them after kind of the constellations they're found in. And then the vertical axis is the star formation history. So when across the age of the universe were these stars formed? And you can see with all of them, they formed all of their stars by about 10.5 billion years ago. So they haven't been doing anything for 10.5 billion years. And to give a little context, we think the universe is only about 13.5 or 13.7 billion years old. So they were real busy for a couple of billion years, and then they've not done much since then. So that does mean that they haven't really done anything since the early universe. And one thing that's really interesting that we looked into a lot, and this is some of the work that I did as a grad student at UC Irvine, was to see what shut off the star formation in those galaxies. Like, why did they just stop forming stars all at the same time, even if there's like 50 of them. They just stopped. Part of it could have been, well, if they're a galaxy or if they're a satellite of the Milky Way, there's something about being a satellite of the Milky Way that they all shut off their star formation at the same time. This would mean that they would have to have all become satellites of the Milky Way at the same time, right? So a lot of my work in graduate school was looking at something that we call dark matter only simulations. These are giant simulations of like the entire universe or little tiny boxes within the universe. They visually look like this, where every single dot that you see there is a dark matter halo or a clump, a sphere of dark matter that we can kind of characterize as having a galaxy inside of it. The larger videos are so short. The larger dots, the red dots, those are larger galaxies. So this would be like the Milky Way, or this would be like Andromeda, and maybe this one would be the Milky Way, and you'd have some of the large and small Magellanic clouds would live in some of those smaller red dots or dark matter halos. And so what I did was kind of dive into these, into a whole range of them, and tried to kind of figure out if these ultra faint dwarf galaxies, so the smallest dots in this video, if they became satellites of the Milky Way all at the same time before 10.5 billion years ago, and they did not. So we can say that they really haven't had much evolution since the early universe. They shut off, maybe they shut off their star formation all around the same time. Maybe they became satellites of the Milky Way or some larger galaxy, during that time or after that time, but that didn't impact the way they evolved throughout the history of the universe. So they've had no evolution or not much evolution since the early universe. So this last criteria, and this is where I think it really gets, I've been really excited about the work that I'm currently doing right now. We know they've had some interaction with the Milky Way because there are satellites, but how has that impacted them, right? And so we can turn to elements, basically the periodic table of elements, to kind of figure this out. If we look at the amount of elements, of different elements within these stars, it really gives us a peek into the actual like evolutionary history of these systems, of these ancient systems. This is because we know how every single element on this table is made. There's some of them that are, human made, right? There's a few like hydrogen and helium that were created like in the Big Bang as the universe came to be. You had hydrogen and helium. Little bit of lithium, you could argue that it was made in the Big Bang. But with everything else, they're all made in like inside of stars or as stars are dying. So when supernovas go off, there's new elements that are formed all the time. Some of them are really kind of rare and they're only made when like neutron stars merge together. There's a lot of energy in that merger that creates new elements. So all of us, and this is where I hope you've all heard Carl Sagan saying that we are all stardust. This is why we are all stardust. Everything that is made, that makes us, is made in dying stars. So we can use these facts to kind of piece together what these galaxies have been doing over the course of history, really. And I'm doing this right now. I'm finishing up this work looking at 10 stars in an ultra faint dwarf galaxy called Hydrus 1. So this is just, again, another kind of sky map showing where these stars live within this galaxy. These are the 10 stars that I'm looking at. And this is kind of the result of that work. So I was able to we do this by using something called spectroscopy. And it's really just like using fancy prisms. If you remember the kind of pyramid, long, weird pyramids from like grade school, and you hold it up to the sun, and the sun comes in one side, and out the other side, you get that beautiful rainbow. We do essentially the same thing by pointing a telescope at the stars, and it sends all of the starlight through the telescope, and then we just stick a special kind of prism in there that it'll separate out the light, and then we analyze what that light tells us, because every element gives you a different kind of spectrum, right? It gives you a different set of light. So something like carbon, we can look at carbon in every single star and kind of compare the carbon within Hydrus 1 to all of the other stars in other ultrafaints. And as you can see, so those background gray dots are stars and other ultrafaints. The bright color, or maybe they're not bright, but the colorful markers are the stars in Hydrus 1. And when you compare the two, they all look the same, which again is telling us that these stars, these galaxies all formed in the early universe and have really had the same kind of path throughout the universe, throughout 10 billion years of living. They all still look the same, which is really cool. There's other exciting elements, like we love carbon because, you know, we are carbon-based life forms. But there's other really exciting elements like these strontium, barium, and europium. I don't think about them much in day-to-day life, but they're formed in this really very specific way. It's something called a rapid neutron capture process. It's a lot of words to just say that there has to be a lot of energy involved in the creation of these types of elements. So that means that they are likely formed in supernova, so giant stars dying, which means that we had supernova going off, or giant stars exploding in the early universe, creating these elements that now we see in these 10.5 billion year old stars. And so that's why with some of these, even though we don't have great kind of constraints on them, we still really spend a lot of time kind of digging into them to learn about what the early universe was like, because we see these rare elements inside these old stars. One of the other things that I really like to do is compare the elements to one another. So if we go back to our periodic table, let's look specifically at magnesium and titanium. Magnesium is primarily formed in dying kind of high mass stars. So they're going supernova, but not they're not the most massive stars. And titanium is primarily formed in something called white dwarf supernova. White dwarf supernova are fun. If you have a white dwarf and you have a partner star that's any other kind of star, if they're close enough together, the white dwarf has so much mass that giving it a lot of gravity, it starts stealing matter from its companion star, from its binary star. It just keeps stealing from the bigger star. And at some point, that white dwarf can't hold on to that anymore, and it just goes supernova. Like, it dies because it stole so much. Being greedy is not good anywhere in the universe. This is how titanium is formed, when a white dwarf steals too much from its partner. But these are two different really cool cosmic events that are creating these different elements, right? And we can kind of look at the comparison of how much magnesium is in the star versus how much titanium in the star to learn more about the kind of rate of these events in the early universe. And what's kind of fun is that we see this in a really interesting way in Hydrus 1. So this figure, and I realize I apologize because I didn't really explain these kind of plots when I first showed them. So this vertical axis shows us the magnesium abundance, divided by the titanium abundance. So that's just our ratio. The horizontal kind of axes here shows us iron versus hydrogen. We call that metallicity. Astronomers have a special way of talking about elements, and if it's not hydrogen or helium, it's a metal. It's just a silly cultural thing we do. So if it's not hydrogen, it's not helium, we call it a metal. There's so much iron in like every star that we use iron as kind of a proxy or a way to talk about how much all elements are in those stars. And because our ultra-faint dwarf galaxy stars are very old, we can think of their metallicity or their iron to hydrogen abundance as being kind of like their age. So these two stars here that have higher metallicity, they're actually about the same age. So they were born about the same time in the galaxy, but you can see they have very different ratios of magnesium to titanium. This may actually be a little bit of a hint that there was something that we call inhomogeneous metal mixing in the early universe. Or to put it in the terms that we were talking about a moment ago, there was different star formation events going on in this galaxy at the same time. So you may have had a high mass dying star go supernova and a white dwarf supernova happening at the same time in the galaxy. And those explosions didn't really mix around the entire galaxy very well. So they kind of stayed localized in a sense. And because of that localized or inhomogeneous metal mixing, they didn't thoroughly mix all the way through, you get these different ratios of elements in these stars in this same tiny galaxy. And this is, we think it could be this. We need more data to really tell. But because if you see this kind of top more magnesium rich star here is on the outskirts of the galaxy in the map, and this more titanium rich star is on the kind of opposite outskirt of the galaxy. If those two stars throughout their orbit stays in those kind of opposite positions, this could be evidence that there's multiple star formation events happening in the early universe. You have white dwarf supernova going off, you have high mass stars dying, and they're not mixing up very well. That's a really awesome like physics playground to learn about how stars and gas and dust and everything is forming in the early universe. I mentioned that we really need to like focus we need to do better data. These error bars, vertical error bars here, are overlapping each other because we don't have fantastic data for this star. So hopefully with this paper I'll be able to go get some more data and kind of dive deeper into what's really happening in this galaxy and why we're seeing differences in abundances, even though these stars are essentially the same age. So we haven't really answered that question yet. We know they've had some interaction with more massive galaxies like the Milky Way, but we don't really know yet how much these more massive galaxies or different star forming events, different environments that the galaxy is growing in or stopping its star formation in. We don't know how much that's impacted the galaxies because we just don't have that much data yet. So this is still really a young field and something that's really giving us fantastic insights to kind of go along with what we're learning through wonderful missions like the James Webb Space Telescope. So I would love to take questions and to chat more about this. As mentioned earlier, you can reach me on, I forgot to change that. I just deleted my Twitter or X account recently. I'm sorry. But you can find me on Instagram. I live on Instagram. I'm also now on Blue Sky, and you can email me as well. And I may need to change that email, but I can like email it out to y'all, or I can put it in the chat, I guess, and we can share if you want to get in touch. I'll stop rambling, and I'm happy to take questions.
Thank you so much for that presentation. That was awesome. So does anyone, yes, does anyone have any questions?
Hi, so I'm an avid amateur astrophotographer, and we've seen a number of presentations prior to yours that largely involve citizen science. And I know that a lot of your data comes from space telescopes, but is this something where an amateur telescope, someone like me who does long exposure photography, where stuff that I capture might be of use to you?
So this is something actually that I've been thinking about a lot, because with the way that we get our data, or the way that I get my data, is using like the Keck telescope, which is 10 meters, or the 6-meter telescopes in Chile, and staring for 8 hours. And we get okay data. So the spectra we need, it's really hard to get. But I've been thinking more and more, like I now, so these are my two, I have a 17-inch and a 24-inch telescope in San Bernardino that we're trying to think about using. Right now, there's not much that we can glean or even really see with smaller telescopes, but there's a lot of work that we need to do with kind of marrying citizen science and these larger data sets that we're getting. So y'all have likely heard of the Vera Rubin telescope and the Legacy Survey of Space and Time, the LSST. That's a telescope that will be coming online in 2020, in like just in a couple months, actually, probably end of the year. It's going to be taking like a petabyte of data a night. And there's going to be so many things that we're trying to look after that it would be so awesome to have, citizen science, like avid astrophotographers like you, kind of be able to go and follow up on some of these things. So unfortunately, right now, there's not many possibilities, but myself, and I know a lot of other folks working in this kind of dim space are really thinking about more, because I think we're missing out on the opportunity to work with y'all.
You mentioned Chile. Is that the ALMA telescopes that they have there?
It is near Alma.
Okay.
So I think they're both in the same desert. I think it's the Serrano Desert. It's like fantastic for astronomy because it's really dry and it's really high and there's nobody out there. So there's a ton of telescopes out there. This one is a brand new telescope it'll be called the Vera Rubin telescope. I think it's near Alma though.
Got it.
Hi, just curious about the halo, the dark matter that surrounds our galaxy and the formation of these dwarf galaxies. There any relationship, or do you have any opinion what that dark matter is based on your knowledge?
Yeah, so I do think it's some new type of matter that we just can't see. And maybe not necessarily new type of matter, but I think it is something like fundamentally different with the way we understand the world now. And a lot of the reason I think this is because we don't see anything from it. And there's a lot of work. We know that we, or what we call baryons, anything that you can see, it interacts gravitationally with dark matter. Like dark matter affects the way that things that we can see, their velocity, the way that they move, but there's nothing else that we understand so far. So I do think it's something new. Like it's not a bunch of black holes or dead stars or something like this, which are other kind of ideas of what it could be. It's not a very exciting answer. I'm sorry.
Thank you. We do have a question in the chat from Charlie. Have we learned anything new about the formation of the universe from the examination of ultra-faint dwarfs to date?
Yes. So one of the things that we've really kind of learned about is that maybe the biggest thing is that we know less about stars than we thought we did. And a lot of this is because theoretically, the first stars that ever formed, if there was only hydrogen and helium in the universe, then the first stars that ever formed should only have hydrogen and helium in them. So they should be these zero metallicity stars, right? Nothing but hydrogen and helium. And as stars, burn hydrogen and helium in their core, they start making new elements, and then they explode, and those elements go out into the universe. And that's why kind of every generation of star after that has more and more different types of elements. These stars that we're seeing are, at least 10.5 billion years old. We thought that it would take much longer for stars to that first generation of stars to have died and created the second generation than what we're seeing. We know in the ultrafaints, we're seeing at least the second generation of stars ever formed, and they're ancient. So that means there must be things, either stars are dying much quicker than we realize, than our theories say, or there is something like fundamentally different about the early universe that was causing those first generation of stars to like live their lives and die very quickly to make this second generation that's still very old.
Yeah, very interesting topic. I never heard of this before. Thank you very much. I have a couple of questions. One is, all the 50, 60 UFDs that you talked about that have been identified, all of them are in the Milky Way, or there are any other galaxy?
So we've now seen 5 that are around Andromeda, the Andromeda galaxy. So Andromeda is the closest galaxy to us that's about the same size as us. And we've seen about 5 there. This was literally in the past like 2 years, and no one's really convinced that they are dwarf galaxies. They may be star clusters that are just far enough away that we can't really tell. And there's one that is technically not a satellite of the Milky Way, but we're not convinced that it wasn't once a satellite of the Milky Way and just left our dark matter halo. So a lot of people study that one. It's called Eridanus 2. But aside from those 6, they're all within the Milky Way.
Thank you. The second question I have is, you've been working on, you're focused on Hydrus 1. Are there other people who are interested in studying other UFDs within Milky Way? And are there any similarities between them, among them?
Yes. So there are. There's a handful of 20-ish other folks around the world who really kind of look at these detailed chemical abundances, as we call them, in the ultrafaints. And there are, the majority of them, Hydrus 1 is one of them, the majority of them are all very, very similar. There's a few kind of special ones that we've seen. Reticulum 2 is one where its chemical abundances look fairly similar to all the other ultrafaints, but we've been able to see stars within Reticulum 2 that are much further out than all of the other galaxies. So you could think of Reticulum 2 as being kind of squashed in a way, which may show that it had more interactions with more massive galaxies than we thought before.
Okay. And the explanation that you gave, that these are the relics of the supernova or the Big Bang, is that the only possible explanation, or is there any other possible explanations?
So we think that some of them, at least, are relics from the first galaxies ever formed. But there could also be, we're realizing that, especially with something like Reticulum 2, some of them may be like remnants of more massive galaxies. So as galaxies are kind of going around, they merge together. Sometimes as two galaxies are merging, a little like nugget of a smaller one will get shot off in the merger. So the majority of the two that are merging together will form one, but there can be little like offshoots that just spit out in the merger. And those we would think of as remnants of galaxies. And so it's a possibility that some of these are not true relics because they've been much of their mass has been lost in a merger or something. Yeah.
On the topic of like calling them dwarf galaxies, I find that what separates star clusters from galaxies is mostly what's contained outside of stars in them, like maybe like planets or like asteroids or meteorites. So my question is, could there be a possibility that some of these dwarf galaxies could have dwarf planets or any kind of planetoid like rock material within them? And if that's the case, could they also be capable of showing us how many like planetoids could be in a dwarf galaxy that could help us estimate how many planets could be in a regular Andromeda galaxy, for instance?
Yeah, that's a fantastic question. And I think it would be the coolest thing if we found like an exoplanet in an ultra faint dwarf galaxy. I think it's possible. Like, even with our kind of models of what the early universe looked like, planets form almost at the same time as stars do, right? Stars form from this kind of cloud of gas and dust, and kind of what's left over from that cloud after the star has formed, that's what becomes planets. So there's not really a reason of why planets shouldn't exist around these very ancient stars. Unfortunately, they're so dim that our current methods of really detecting planets around other stars are not advanced enough to see the like tiny dips in light. One of the primary ways we detect exoplanets is if you have a star and the little planet passes in front of the star or between us and the star, and there's a little tiny dip in the light that we're collecting from the star as the planet passes in front of it. Our ultrafaints are so dim that we don't really have the like sensitivity in our instruments to be able to see that little tiny dip of light.
Makes
So
sense.
theoretically, yeah, I think it'd be fantastic if we could see it. I just don't know if we have the capability yet.
Well, if you do find the capability, would part of your first priority would be to find these planetoids or exoplanets, or would the first
Yeah.
priority?
Oh, yeah. Oh, sorry.
Or would the first possibility being to see if any like life could exist within these star clusters? Remember, we're talking about stars that are so close and combined together. Like the heat from these stars must be very extreme compared to the heat from our sun, for instance.
Yeah. So I think with ultrafaints, because their stars are dimmer, so they are a little bit cooler. So I think we would definitely like it would the first priority would be to see if we can find an exoplanet, and then like it would be I think most folks that work in exoplanets would really be excited to characterize it. Like, is it something rocky, terrestrial, kind of like Earth? Does it live in the habitable zone? That sort of thing. And the models that we currently have for what type of planets could host life, at least carbon-based life like ours, are really like robust in the sense that they could take it all the way down to that very faint dim star level to almost be able to tell right away if we find something. If we have the capability, we go look, we see something, we could characterize whether it could possibly have life or not.
Hopefully it happens one day.
I hope so too.
Agreed. Dr. Rodriguez Wimberly, thank you so much for your time. We truly appreciate it.
Thank you. I'm so happy to have given it. Wonderful questions. Thank you all so much.
Thank you. I think I'll
Click right on it and then we'll be back.
I think I'll breeze through our typical agenda. I won't go through the conditions overview. It's clear. The moon won't be out until, it looks like midnight. Yeah, 12:41. We're going to try to see if we can take a look at Mars and Jupiter in a moment when we go outside. Anything else here? No. Just quick things. UACNJ opened up a couple weeks ago, so they're back doing their weekly programs every Saturday at 8 o'clock. They're out in Jenny Jump State Forest near Hope, New Jersey. It's a free weekly program. They do a presentation similar to what we do here. And then afterwards, they have about 6 or so, I think more, observatories that they open up as long as the weather's good and the sky is clear. And so I highly, highly encourage it. It's not too far away, but it's far away enough from the city lights that we suffer from here. So certainly consider it. I know I'm constantly checking the weather for Saturdays and seeing if it lines up with a free Saturday that I might have. The East Brunswick Symphony Orchestra is having an event, the May the 4th Be With Us concert, happening on May 4th. May the Force be with you, May the 4th. All right. It's happening at 3 o'clock at the East Brunswick Magnet School. And they'll be playing Star Wars music. And they do have pre-concert activities beginning at 1:30. The East Brunswick Astronomy Club will be present. We'll be showing sunspots and the moon, as long as it's clear, through a digital telescope. So be sure to look out for that. And then for our May meeting, we do have a presenter. Our meetings moving forward, as long as we can, will be hybrid. So they'll be in person at the East Brunswick Public Library, as well as live streamed through Zoom. So for everyone on Zoom, welcome. Thank you for joining us for our, I think, maybe second Zoom meeting, first hybrid meeting. But we will hear from Dennis Cheng, who has attended a couple of our meetings. He's going to do an introduction to amateur astronomy. And you can check that out on the East Brunswick Public Library calendar. We typically meet for some newcomers the third Thursday of the month. Just really quickly, did anyone catch the partial solar eclipse that happened Saturday, March 29th? I can't blame you. Huh? Did you try? Was your view just obscured by buildings and trees? Yeah, it's really hard because right as the sun was coming up is essentially when we were going to be able to see the eclipse. And unless you have a really unobstructed view, you weren't really going to see anything. And it only lasted for us here, what looks like it started at 6:45, ended at 7:04, 15, 20 minutes, right? So it was a really, really tight window, but I figured I'd ask. I'm happy you tried. In August 21st, we are having a quick fire presentation. So if you are interested in giving a presentation to the Astronomy Club and you want to do it in a sort of no pressure scenario, we are doing this quick fire presentation where the hope is we'll get a bunch of people and do just a quick 5-minute presentation on an astronomy related topic. Just giving folks from the club an opportunity to present for us. So if you're interested, My email is up there, as well as the evastro.org. Just reach out to us, let us know if you're interested, what the topic will be, and we'll slot you in. And then lastly, really important, in June, our meeting will be moved. It's not going to happen on the third Thursday of the month. It'll be on June 5th. It's still a Thursday, but we did have to move it. So with that said, please make sure that you're signed up for our newsletter. We only send a newsletter out once a month. We don't spam you. But also follow us on Facebook and Instagram. It's the best way to stay on the know of what's happening for our meetings, what events we're going to. So if you're interested, by all means, follow us on these platforms and sign up for our newsletter. It'll just help you be in the know as to what we're doing. I normally don't rush through it, but I really do want to get outside with the telescope. So with that said, let's go outside.